The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay. Well, last time I had a long and complicated set of notes, and I'm going to start somewhere near the middle of those to try to give a little bit more perspective on what's going on here. We're trying to develop the machinery to describe vibrations in polyatomic molecules. And the Wilson F and G matrix approach is especially beautiful because it focuses on the little parts of the molecule that we're interested in. That we know that molecules behave with local units, and what we're going to try to do is build up a description of vibrations focusing on the local things, which are if you have a CCH in a molecule, there are lots of molecules with CCH in them, and a lot of those things just transport from one to another. The purely numerical approach is just that. It's a purely numerical approach. It will describe everything, but it won't allow you to use chemical intuition. It won't allow you to zero in. Well, it will, but in a more indirect way. And so I think it's really important to see the microscopic treatment. So let me begin again. We have several sets of coordinates. We have the Cartesian displacements. We have the mass-weighted Cartesian displacements. We have the internal coordinates. And we have the normal coordinates. And we want to get here. But I was just singing the praises of these things. These are the building blocks, the internal coordinates, the bond stretches, the angle bends, the torsions. These are the things that we would expect to be able to move from one molecule to another. These are the things that are the natural place where you put in isotopic substitution. And so this is the path. Now there's two, to get from here to here, we have the square root of the mass matrix, which is a diagonal matrix. Here we have a matrix called the D matrix, which is something that's complicated, that comes from vector analysis. And we really want to work on that. But for the time being, we'll just say there is a D matrix that describes this, and we'll deal with that later. And then there's a matrix, a transformation that takes you from the normal coordinates, from the internal coordinates to the normal coordinates. And they all have names, and there's even another path, and that's the B matrix. So all of these things are involved. This is 3n dimensional, this is 3n dimensional, this is 3n minus 6 dimensional, this is 3n minus 6 dimensional. So these transformations involve matrices, some of which are not square. And there's a little bit of counterintuitive stuff that you'll encounter. Now, in all of this, we have two matrices in which the critical information about the force field, the force constants, the second derivatives of the potential, and something about geometry, masses and geometry appear. And everything about the vibrations come from these two matrices. For the time being, I mean, it's reasonable that there should be a matrix associated with potential energy and another one associated with kinetic energy. And, but we don't really know off the top of our heads what the G matrix is. It happens to be this thing that is really at the core of our understanding of how we get from simple things to the internal coordinates. And I'll show this, or at least I will show that it makes sense to replace this thing that appears naturally in the analysis of the problems by this thing that just makes it more compact. And we call it the G matrix. But the thing that we really have in there is this one. OK, so. And it would be good if there were questions. Not that I believe that I'll be able to answer them, because this is hard. But you know, I've been working on these 2 lectures now for quite some time, and I understand them a lot better than I did for the last 12 years. But I do not think I understand the material deeply enough. So anyway, to get between the various representations, we write equations like this. Now remember, this is not quantum mechanics. These are not Braz-Ketz. This is just a way of describing things that is a shorthand for matrix multiplication. And we know how to do this so well for quantum mechanics that it acts as a sort of a mnemonic for all these transformations. OK, so this dm is just b. B is the thing that takes you between the Cartesian displacements and the internal coordinates. If you have an equation like this and you want to write the inverse of it, well, you just write it. That's one of the beautiful things about this notation. You don't have to do any work. Eventually, if you can define some of the matrices, the computers can find the inverse of the matrices and all that sort of stuff. So it's very, very powerful. And you don't think about the calculations. You think about the structure of the calculation. And that's a wonderful thing. OK, so how do we write this? Well, we want the inverse of this. And when you take the inverse or any operation on a matrix product, you reverse the order. And so we want dm inverse on S, and that would be OK, so there's just a few rules you have to learn for how to manipulate these symbols. And it's really wonderful. And then you manipulate them. OK. So our goal is we know we have kinetic energy and potential energy. And we want to find some representation for both of them simultaneously, one representation for both, in which both the kinetic energy and the potential energy are simultaneously separable. So we want to have some kind of coordinates where we don't have cross terms.
Cross terms between what?
Between coordinates. So we'd like to write the kinetic energy as a bunch of squared velocities. And we'd like to write the potential energy as a bunch of squared coordinates. No cross velocities, no cross coordinates. And we ought to be able to do that. And the normal coordinate representation is precisely that. We want to get there. But right now, we're just playing around with the various representations in order to get a way of imposing the we want to write an equation of motion, which we solve. And that's going to be the Lagrange equation of motion. And we could just as well have done this in terms of the Hamilton equation of motions. We could just as well have, I don't know if I could have, because I don't know where I would find it, so I could copy it down and repackage it for you. But the Lagrangian is expressed as something in terms of coordinates and velocities. And it doesn't matter what coordinates, it's just, it's a way of writing the relevant quantities. And so we express the kinetic energy in terms of velocity and the potential energy in terms of coordinates. And the equation of motion that needs to be solved is the total derivative with respect to time of the partial derivative of the Lagrangian with respect to velocities. So this is kinetic. This is related to the kinetic energy part because this is it's a partial derivative and the velocities only appear in the kinetic energy. And then we have partial of the Lagrangian with respect to coordinates, and this is clearly the potential energy. So we have two terms, kinetic energy, potential energy. This is the same thing as F equals ma, but written in fancy language, and that's good. And so these are the things that we're going to be trying to manipulate. Okay, so let's begin by writing the kinetic energy in terms of things we know and then getting them into a different representation, and we'll play around. And it's very confusing, the number of things that we do. Okay, so we have the Cartesian velocities, so twice the kinetic energy. Well, kinetic energy is 1/2 mv squared, and so we put the 2 out in front, and that's the fancy way of writing the kinetic energy. Remember, this is 2 now matrix multiplications. And we know the rules for doing this, so that it's beautifully elegant and compact. And since it's so complicated, the whole analysis, you really do want a way of making the steps really simple looking. Okay, so now we know that the Cartesian velocities can be related to the mass-weighted velocities this way. And so all we need to do is, if we want to re-express T, the kinetic energy, in terms of the mass-weighted Cartesian velocities, we just plug in now this quantity here, and so we have 2T. We're getting rid of the size, and we're replacing them with Q's, so we might as well put in parentheses like that. We've changed variables, and now we have Q dot m minus 1 m minus 1/2 minus 1/2 Q dot. And that's just Q dot Q. What we wanted. This is simple. That's just a simple sum over I of Q I dot squared. So this is a separable form, the kind of thing we'd like. So what are we doing? It's so trivial to get T in a simple separable form. But the problem is we have to get T and V in simple separable forms simultaneously, and that's not so trivial. Okay, so mass-weighted is just a convenient way of making all the masses disappear, but we know they're lurking. And I should have put a star on here to indicate complex conjugate, but coordinates are real, and almost all the quantities in here are real. And so I probably will neglect occasionally complex conjugating. Okay, so we've done our duty with T, at least for the time being. Now let's look at the potential energy expressed in terms of the mass-weighted coordinates. Well, but what we really want is the potential energy expressed in terms of the internal coordinates. And we know that the internal coordinates are given by dq. And so what we do is we first write this what am I doing? Oh, you see, if I don't look at my notes, I'll do something stupid right away. So we're going to, all right. So we would like to be able to write the potential energy in terms of the internal coordinates. And so we're going to write a power series expansion. And so we have the all of the internal coordinates or internal displacements 0, and then we have the sum over t of the partial derivatives of the potential with respect to each of the functions. Now, this just is a shorthand for at equilibrium, but it's mathematically inelegant and incorrect to use this notation, but I do. And then we have the second derivatives. Okay, and so we say that's enough. Take that away. Now, we just choose our 0 of energy, and that's 0. That goes away. We choose to find, we want to define the minimum of the potential, and at the minimum, the partial derivatives, the first partial derivatives are all 0, and so this is gone for all t. And so what we have left is this, and that's just called ft prime. So we're defining the F matrix in terms of the internal coordinates. The F matrix is going to be of dimension 3n minus 6 by 3n minus 6, as opposed to what the quantum chemists would use, which would be the little f matrix expressed in terms of the mass-weighted Cartesian displacements, and that would be 3n by 3n. And in this modern day of computation, we don't care what the dimension of things are. We don't care about factoring. These are small dimension problems for the kinds of molecules and so removing 6 degrees of freedom or taking advantage or not taking advantage of symmetry, it's not of great consequence. And so, but yet we're building all that in here. Okay, so we can write the potential energy in terms of this F matrix, and the shorthand for that is going to be SFS. So by choosing the 0 of energy at the minimum of the potential and exploiting the fact that we are at the minimum, we get rid of these two terms, and the potential energy is SFS. Now, this is not a simple separable form, so what we want to do is we want to put this in simple separable form, and we want to somehow do the same thing for the kinetic energy. Now, we're going to stick with S as the variables, and so we have to re-express T in terms of S. And so we saw before 2T is equal to Q dot Q dot, but S dot is equal to D Q dot. And so we can rewrite this, we can back transform to S. So let's do that. So d minus 1 s is equal to q. And so we can simply rewrite things. 2t is going to be equal to s dot d dagger minus 1 d minus 1 s dot. Okay, all I did is I exploited this. We could take the time derivative of both sides of this equation. D is not time dependent, and so we have this. And we just call this G minus 1. And if this is G minus 1, D dagger minus 1, D minus 1, then how do we write G? Well, we want something that if we multiply this by it, we'll get the unit matrix. And so we'll see that it will do the job.
I have a question.
Yes?
Why isn't it D minus 1 dagger? Or is that the same thing?
It's probably the same thing. I can't answer that question. That's a good point. I don't know the answer. Josh, does it matter?
Is D a square matrix?
D is not a square matrix.
But it's going to matter.
What? It is going to matter.
I think.
Okay. It doesn't matter for this derivation because I'm making an even number of errors. Or, I mean, so, but I think I have to worry about whether you take the inverse first and then conjugate. I think you're right. It has to be the other way. But I don't think it matters. For this, this is true.
Okay, I see. If you define it, if it's defined as D dagger, then G minus 1 would have to be D dagger minus 1. D minus 1. Right?
Yes.
I think it's right. I think I was just getting confused.
Well, I don't think you're confused at all. I think that was a really profound question. When you're manipulating things that you don't choose to understand, it's easy to make an error of packaging. And but you can check my tracks. And now the notes for last lecture and this lecture are both extensively revised on the web. So what you have is riddled with either errors or infelicities. Okay, so we now have the ability to write the kinetic energy and the potential energy in a very compact representation, which is not our target, but we have the same variables, the S and S dots, and we have G and F, these two matrices. This is very convenient now for inputting into the Lagrange equation of motion, which is what we will use to be able to solve the problem. Okay, so the Lagrangian is T minus V, and so we can write this in compact form as the sum over I and J of G minus 1 Ij Si dot Sj dot minus, so this is sum here, F Ij of Si Sj. Okay, you can see how this is wonderful because we're told to take partial derivatives with respect to S dot and with respect to S, and we're supposed to take a total derivative with respect to time, and this is going to make this simple, and we'll get our secular equation. the thing that we have to solve in order to write everything out. So we write the equation of motion, and so what we get is that 0, and I'm not going to write all the steps, is equal to a single summation of G minus 1 Ij Sj double dot plus, that can't be plus, it has to be minus, Fij Sj. So, oh, I see what I did. Okay. So this is the equation of motion, and you'll notice that we have a sum over, well, we have a whole bunch of equations for 3n minus 6 different values of I. But each equation has pairs of terms where you have derivative related to the second derivative related to the value times a constant. It resembles 0 is equal to x dot dot minus ax, which is the equation for harmonic oscillators. So what we do is we say, okay, let us assume that each of the normal coordinates is a harmonic oscillator. Each of the internal coordinates is a harmonic oscillator. And further, we say that we can write them as, so this is S of t, cosine lambda to the 1/2 t plus epsilon for j equals 1, 2, 3n minus 6. So we have all of the internal coordinates expressed as harmonic oscillators. Yes?
Shouldn't it be plus Fij Sj in that secular equation? This, no, right there. I guess it should be plus. For getting that cos solution, it should be plus. Derivative is minus.
You're right. Because we want to have these two terms canceling. And so this is going to be, yeah. So is everything okay now? Yeah, all right. So one of the important things is that we have all of the internal coordinates expressed as having the same frequency and same phase. So this is an assumption about the form of the solution that we have to discover whether it can work. I mean, we can adopt all sorts of trial solutions, and if we do something stupid, we'll end up with all of the a's equal to 0. Or we'll end up with too few a's not equal to 0. So this certainly has the right form. We put it into the equation of motion, and so substituting this form into this equation of motion, we have 1/2 cos lambda 1/2 t plus epsilon times the sum j equals 1, 3n minus 6 a j f I j minus g lambda gij minus 1. So here we have a set of 3n minus 6 linear homogeneous equations And in order for there to be a non-zero set of A's, a non-trivial set of A's, we have to solve a secular equation. The determinant of the coefficients has to be equal to 0. And so that says that this must be true. F minus lambda g minus 1 is equal to 0. This bar means determinant. Okay, and so this is the secular equation. But we do another trick. We know that if you have the product of two matrices, the product of two determinants, the determinant of the product is equal to the product of the determinants. And so we can multiply this secular equation by, on the left by the determinant of G. And so when we do that, when we multiply on the left by the determinant of G, we get a new secular equation, which is the one we choose to solve. And that will be 0 is equal to GF minus lambda unit matrix. This is the secular equation for vibrations. So we multiplied this secular equation on the left by the determinant of G. We could have multiplied it on the right. If we did, we'd get a different secular equation. It's very tempting to say, well, FG, GF doesn't matter. It does matter. They're not the same matrix. And this is still not quantum mechanics. We're not worrying about commutation of operators. They are two big, ugly things, and GF is not equal to FG. This is the one we solve. We could have solved the other one. We would get different, we'd get the same frequencies, but we'd get different normal modes. So this is what we're going to look at. So in order to solve this problem, we have to diagonalize GF. Now we're used to looking at a problem and saying we have a real symmetric matrix. If we have a real symmetric matrix, then you can diagonalize it using a unitary transformation. A unitary transformation is one where the inverse is equal to the conjugate transpose. Well, this is not a real symmetric matrix. G is a real symmetric matrix. F is a real symmetric matrix. But the product is not symmetric. And you can demonstrate that simply by writing a typical pair of 2 by 2 matrices and writing it out, and you'll see that the product is not symmetric. So you're not going to be able to diagonalize this by taking the usual shortcut. You can diagonalize it, but you have to define a similarity transform So there is some matrix L, and it's interesting. I used that name for a matrix before. And we're going to have to prove that this is, in fact, the same L that we saw before. This GF is diagonalized by a similarity transformation, L. Now, GF is square, L is square, so there's nothing fancy there, but GF is not symmetric, so the L inverse is not L transpose. Okay, so now if we could write GF, then we could ask a computer to diagonalize it, and the computer would do so, and it would tell us the rows and columns of the matrix that diagonalized it. And if you wanted it to calculate the inverse of that matrix, it would do that too. So there isn't anything mystic, but we don't know what G is yet. Okay, we will know. It's not complicated. Well, it is complicated, but it's not. Yes. Okay. So this is the equation that has to be solved, and these things are related to the normal mode frequencies. Nu sub k is lambda k square root over 2 pi. And since in vibrational problems we use omegas in reciprocal centimeter units, that's nu k over c. So these are in reciprocal centimeters, these are in reciprocal seconds. Okay. We started the whole formal derivation of the normal modes by saying we could get from the internal coordinates to the normal coordinates by this transformation L. And we could also write this in standard form where so to get from the internal coordinates to the normal coordinates, we want the inverse L matrix, and we want the jth row of the inverse L matrix in order to do this. Okay, so now let's see whether this L is the same L as this L, or let's see whether we have internal consistency. We saw that we could write, well, I'm sorry, we would like to have the kinetic energy expressed in a separable form in terms of the velocities of the normal coordinate displacements. These things are given in terms of the s dots, and we can, I'm skipping steps, but s dot is going to be g minus 1 s dot, because s dot is equal to L q dot. Okay, so we can do that. And then we can go back and rewrite so this is what we want. This is the where did I have that? I said the wrong thing. Where did I do this? This I did at the beginning. And so I then go back to the q dots, and so I replace this, and I have L dagger G minus 1 L q dot. Okay, so what we would like to be able to show is if L is the thing that takes us between S and Q, this thing has to be equal to the unit matrix. So okay, we can rewrite that by multiplying on the left by the inverse L matrix as so this is an equation that is equivalent to that, and Okay. And we have the kinetic energy, the potential energy, Q lambda Q. And we saw before that we could also write the potential energy as S F S. And replacing S with Q, Q L dagger F L Q. So we would also like to be able to show that L dagger F L is equal to lambda. This is a point of great confusion and disturbance because this looks like our usual unitary transformation. These lambdas are not the eigenvalues of F. They're the eigenvalues of GF. This transformation is a transformation that happens to take F into this matrix, but this L doesn't know anything. I'm sorry, these eigenvalues don't know about this. They know about this jointly with G. Okay, so now what we need to do is to show that this is also compatible. And so what we do is we want to know whether this and that are compatible with the original equation L minus 1 G F L is equal to lambda. So what we do is we replace L minus 1 by this. So we have L dagger G minus 1 G F L. And lo and behold, what we have is L dagger F L, which is this. So all of the equations are consistent.
So is that another sense of saying that the L sort of has information of G embedded in it?
Yes. I mean, the L is defined by diagonalizing GF. Now you can, in fact, I've had a long conversation with Troy, and you can repartition the pieces of G. You can, but it still doesn't make any more sense than just saying, okay, this is what we're doing, and you just have to be careful because this makes you think that you just give the computer the F matrix and it finds the eigenvalues by a unitary transformation. But L is something that's not a unitary matrix. L is defined as something that will diagonalize a non-real and non-symmetric matrix.
So put another way, you have to have the geometrical information in order to get those eigenvalues.
Absolutely.
Yeah.
Absolutely. So now we're at the end of the previous lecture, and now we're beginning to start to go towards how do we get the G matrix, because we sort of know about F. Okay, but now let me just say some cautionary remarks. I want to finish this lecture because there's no sense in stopping before it's over and having to go over the whole thing again. So we have two things that go into a description of the normal modes of vibration. We have the force constant matrix, and we have the G matrix. Where do we get them? Well, we could imagine that we would somehow get the F matrix from spectra. You can convince yourself that the number of independent elements of the F matrix is this. And so then if we say we have 3, 4, 5, 6 atoms, number of elements, number of modes, you can see that we have 6, 21, 45, 78 independent elements of the F matrix. And we have 3, 6, 9, 12 normal modes. So there is no way from experiment you can determine all of the elements in the F matrix. You have far too little information, even if you did a huge amount of work, far too little information to empirically determine the F matrix. The way we get the F matrix is by either taking huge chunks of it from ab initio calculations or setting a lot of the elements in the F matrix equal to 0. If you have two internal coordinates that are not adjacent to each other, it's reasonable that there won't be any appreciable cross terms between them. So one can fill the F matrix with a lot of zeros. This is an approximation, but it's a good approximation. There's also questions of functional groups. Suppose you have a particular group of atoms that are together and you sort of know how the various elements of the F matrix ought to behave. And so you can take them from other molecules. So we know that the F matrix, the force constant matrix, is something that requires a huge amount of information, but we're not too concerned about getting all of it by hook or by crook. Well, what about the G matrix? The G matrix is obtained by some really elegant vector analysis. And we'll just begin on that. So what we want to do is define the various kinds of internal coordinates. So we have stretches. And so we denote them by quantities like this. We have bends. We have dihedral angles. And so a dihedral angle, suppose you had something that looked like this, A, B, C, D, and now you look at it end on, A, B, B, C. It's the angle between the two planes. And that's generally called tau. Okay, now, you draw a picture of a molecule, and you have to decide, well, how do I choose 3n minus 6 linearly independent internal coordinates? And the answer is, it's not easy. But the other answer is, well, so what? Define, just take all of the internal coordinates, have an overlarge F and G matrix. And when we solve for the frequencies, the normal mode frequencies, you'll get a whole bunch of zero frequencies. So that's one solution. Just put everything in.
I thought the F and G matrices were defined to have certain size, 3n minus 6.
They should, yes.
That's for the F matrix.
Yes. But we're talking about internal coordinates, and as soon as we've gone to internal coordinates, we know there are 3n minus 6 linearly independent internal coordinates, but we can have an overcomplete matrix. And
that doesn't mess anything else we've done up before?
I don't believe so. But what the trick is going to be, I mean, is to find how the internal coordinates are enter into the kinetic energy. And that's going to involve some very clever definitions of vector displacements.
I guess one has to be really careful then to make sure the F and G matrices are both overlarge in the same way.
Yes, of course.
Products of them.
But I mean, often when you have redundant internal coordinates, they have the same F matrix element. I mean, so I haven't thought about this carefully, but all right. So what we want to do is now attempt to describe the internal coordinates in terms of things that we can manipulate. And this is the difficult part. And I want to at least say something about them so that we will be able to start next time having at least thought about these things. So we're going to, here is an internal coordinate, and we're going to define it as a sum over atoms of this little thing, ST alpha, dotted into a Cartesian displacement of atom alpha. So part of the reason for defining these things is that this is how we build up the G matrix, but it's also how we impose constraints of no center of mass translation and no center of mass rotations. And so these things are really, really beautiful and elegant. So and we're going to discover, I'm not saying that you're not going to be able to see how this is true, but we're going to be able to write the G matrix as 1 over m alpha st alpha dot st prime alpha. So this is the notation. We're going to figure out what these things are. These are displacement vectors which enable you to impose constraints and enable you to write the G matrix. Okay, let's explore what they are. Recall that we wrote S in terms of the size. So S of t is sum over I b ti psi I. Now we can write this as a power series, and so we say that this is partial of st d psi I at 0 psi I, and neglect the higher terms. Remember, this is displacement, so the when you set when you go to s is equal to 0, well, that's just a 0 here. Okay, so this is the first term in the power series. Now, knowing this, we can write st in this wonderful way. St can be written not as a sum over individual Cartesian displacements, but as a sum over atoms. And we have ds t d psi x alpha psi x alpha dst d psi y alpha psi y plus dst d psi z alpha. Now this x, y, and z is an extra notation that helps to make everything clear. So z alpha. Okay. All right. If we define the gradient vector, you see lurking in here is something that's looking very much like a gradient. So we define the gradient, or we write the gradient for the motion of the alpha atom as partial d psi x alpha unit vector x partial d psi alpha y unit vector y plus partial d psi z alpha unit vector z. And we write the displacement as psi x alpha unit vector x plus psi y alpha unit vector y psi alpha z unit vector z. So these two things together with this tell you that ST is just the sum over alpha 1 to n of the gradient of ST dotted into rho alpha. So what we've done is we've written the internal displacement as a gradient of the internal displacement dotted into the arbitrary displacement. Okay, and then since we have a dot product, we'd like to know, well, what direction do we displace atom alpha to get the most bang for the buck? We want to know, and if this displacement is along the gradient, the direction of the gradient, then we get the largest change. So that means that ST alpha, this little thing, is a vector pointing in the direction that gives the largest increase in ST. So for each atom, we have a vector which is pointing in a direction that says, okay, we move in this direction, we'll get the maximum increase in S. Then the next thing we want to know is, what is the increase? And once we do all of that, we have then a way of defining all of these ST alphas, and then we can use them to do all the neat stuff. So I'll go over that a little bit at the beginning of tomorrow morning's lecture, but it's really astonishing how this works out. Okay.